In this video, we'll be looking at the teacher notes for lesson 26. Correlation does not imply causation. The first concept I want to talk about is this term imply. One important thing throughout our students' study is to know that there's different definitions for each word, and what we mean in the general world and what we mean in a particular field may be different things. And imply in this case is one of those words. When your students will hear a word like imply, they're going to think hinted at or something that is meant that is not exactly said. For us, we're thinking of the logical imply, as in when we make the statement, if P, then Q. We often make a analogous statement, P, and then this logical connector, Q. Another way that we state this is P implies Q. We don't mean P hints at Q or P is subtly stating Q. What we mean is P guarantees Q. If P happens, Q is certain to happen, and that is the meaning of implication in this case. Correlation does not guarantee causation. That is, correlation probably does hint at something going on, but it is not sufficient in and of itself to give us causation. So in this case, we're thinking of implies in the logical sense as of sufficiency. P is sufficient. Okay. Likewise, guarantees. Okay, so in this statement, implication has it's a stronger than just hinting at. So when we're telling our students that correlation does not imply causation, if we see correlation, there very likely is something going on, but it's not enough. It's not enough in and of itself to see some correlation and say that, hey, X is causing Y. All right, so immediately your students may ask, well, what do we need for a cause? If this is not enough, then what does it take to show causation? What does it take to show causation? Well, the short answer is it takes an experiment. All right. And for the purposes of our course, we're not going to, or this one lesson, we're not going to get into all the things that make a good experiment, but you should know that 3 principles of experimentation, 3 keys of good experimentation. Are control, that is, we want to hold lurking variables constant. When I think of control, I think of comparison. We want to have, if we're conducting some experiment, we want to have 2 groups. At least 2 groups, and in these 2 groups we want the subjects, perhaps let's say we have a new cholesterol drug. We want to have 2 groups. One is getting our new cholesterol drug and the other is getting a sham drug, a placebo, or really probably the old cholesterol drug. And we want these 2 groups to be as similar as possible. That way the only difference between the 2 groups is our treatment. So we can tell, is it indeed our drug that is having this effect. So control speaks to good comparison. The second key or principle of good experimentation is randomization. So we have these people and we're going to break them up into groups. How do we do it? Well, we randomize. That is, we use impersonal chance. Okay. Use chance. By using chance, I mean some kind of drawing method. We put names in a hat and we split them up, or we use a random number generator to assign. We don't put person A in this group and person B in this group because we liked person A and we didn't like person B. And we don't, this term random does not mean haphazard, as in I randomly picked this shirt from my closet. No, you went in there and grabbed one of the shirts. If you numbered the shirts from 1 through 10 or 1 through 6 and you rolled a die, that would be a random selection of the shirt. If you go in there and grab one of the shirts, that's haphazard. There's a difference between random and haphazard as we mean in statistics. And the last principle 3, there are other things involved in experimentation, but these are 3 of the most important. Replication. Replication can mean 2 different things. One is we want to use we want to do whatever we're doing to enough people. If our cholesterol drug shows improvement for 4 people, that's one thing. If it shows it for 4,000, that's another thing entirely. So replication can mean large sample sizes. Okay. And it could mean the ability to actually redo the entire experiment. We would hope that our experiment would be done in such a way that some future experimenter could come back and perform it. These are 2 different interpretations of what we mean by replication. Redoing the experiment. And of these 2, this first one probably has a larger, perhaps more importance to us. Having a big enough sample will have much stronger power. Okay. Other variables. You're going to, in the students video, I mentioned this term, lurking variable. In addition to this term, lurking variable, you will also run into the term confounding variable. These 2 terms, some books will treat them, some statistics books will treat them as virtual synonyms. Lurking variable, more frequently you will see it defined as something that has some common effect on both x and y. A confounding variable is a variable that's mixed in. You can almost think of confused. It's entangled in some way, all right? It's mixed in with our response, our y variable, in such a way that we cannot pull out whether or not it was the explanatory that was contributing to it or it was actually this other confounded variable. So these 2 terms, I certainly wouldn't worry about driving them home to your students necessarily, but you can further your studies by looking at them a little bit closer. The big idea, what you really want to pull out, is there are just other variables. There's going to be things other than, and by other variables I mean not our explanatory or our response. Okay, we're for the purposes of our discussions in algebra, we're going to be looking at two variables at most and how they relate to each other. Well, there's a lot of other things going on, and so these other variables could very well be playing a part in this relationship that we're observing.